Hey, everybody. Before we dive in, I want to quickly share that I'm a little, both me and the doggy, I think, are a little under the weather. There's something's going around, I think. So, my hope is we can get through this entire stream a-okay. But if I cut it short, uh, that's probably why. So, today, I want to talk about a few things. One, I oh, look at this. It's not even showing the right screen. Let's see if we can switch this, huh? All right. There we go. I think we're hopefully looking better now. All right. So I want to talk about a few things, mostly listed here, but also a little bit listed here. But let's start with this. The first is, as we've mentioned and discussed many times, I'm a firm believer that directional correctness is far more important than precisional correctness. And a lot of that is just this notion of doing stuff, just going out and doing something, having the courage to try something new or to uh, have a thought that's maybe half baked. And I think when you deeply understand directional correctness, I think you can start to understand how it's okay to not be perfectly correct. And oftentimes, for us to get better at things, a lot of it has to do with just put in the reps, put in the time, and just being okay with things not being perfectly manicured and everything being perfectly rehearsed and edited and all of that other silly stuff. So today we're going to do a quick, well, maybe not quick, depends on how much we meander. We're going to go over a few of these slides, probably just these 10 slides. 11 through 14 are just backup stuff. And I haven't really finished these slides. The second half of this is totally absent. So this part where we're going to explore the open AP problems, I haven't gotten to this. And I'm doing that on purpose because I want to just give you an example of here's some directional correctness where I think that I've got the essence of the first part of the talk that I plan to give, but it's not perfect. And a lot of that, me doing this stream today, is just to show an example, kind of show rather than tell. And so we'll see a little directional, hopefully directional correctness. That's not going to be perfectly curated and beautiful, but hopefully it gets the principles of these things across in a way that makes sense. And anyone that has comments on any of this stuff, feel free to interrupt at any time. I plan to run the talk this way too. So that's sort of the preamble of this, and I feel like that's sufficient. The second part that we'll go over is the content of this early version of this talk. That'll probably be the majority of this stream. And then in closing, I want to share, just for those folks that stick around, one of the most important things that I think can lead you to being able to do, in my mind, really great things. And the spoiler here is it's been my experience and it's my strong conviction that small footsteps and consistency, like doing something like this, doing things that are directionally correct, is far more important than waiting until everything is perfect and only working in spaces that you feel 100% safe in. I think that is that second approach of waiting until everything's perfect and all the pieces are assembled and the universe and all the stars are aligned. I think that if that's what you do, you may be inhibiting your ability to fulfill your true potential. That, as we've discussed many times, I think that a lot of what gets you world-class quality is not that you try once and it's perfect. It's that you try and try and try and you do a bunch of quantity over and over and over and over again. And the result of all that effort is a slow climb to make you better and better and better. But we'll get specifically into this, and I'll share some details on how I view things like giving invited talks at places like MIT. And so a little background on this talk. And by the way, I think it's an open talk. So any people from GTT that are interested in this, I think that you can just connect on Zoom. I think I'm supposed to do that actually. So I'm glad I mentioned this. Just goes to show how far behind I am. Let's not tell the organizers. So this is the Fast Code seminar. And here's me. What is this thing going to be about? It's going to be about all this stuff. Quickly read the abstract. In this talk, we present machine programming, a field aimed at improving the rate and quality in which we develop software. The first part of this talk will explore the fundamentals of MP. That's the part that I think I mostly have sort of figured out. We'll cover the 3 pillars of MP, 4 domains that MP deeply intersects with, and the importance of separation of concerns in MP research and engineering. I kind of changed that last piece, so it's not exactly that, but you'll see. The second part of this talk, which is the part that I don't really have yet, I kind of have it in my head, but it's just not written down. Second part of this talk will explore future directions of machine programming with a specific concentration on aspects related to performance. And I think performance is something that it seems like we're overlooking a lot today, at least in academia, at even the undergrad or graduate level in computer science. And I'll be honest, I think that scares me a little bit, because I think performance, building systems that are performant, is fundamental for their pragmatic adoption. And I think that's part of the reason why language models aren't likely to be adopted ubiquitously. Ben, I'll get into this a little bit. And then this last sentence, our discussion will cover performance considerations of MP systems themselves, as well as reasoning about the performance characteristics of code that MP systems generate and refine. So yeah, I think I'm going to change that a little bit. It is going to be about performance, but and I was kind of getting a little meta there. We'll talk about the performance of the MP system, but then we'll also talk about the performance characteristics of the code that the MP systems are working on. So you're kind of like getting this duality. But I think I want to maybe talk about maybe like the performance of MP systems at scale and the importance of performance for code reasoning in particular. And I think largely I want to focus on that because I feel as though in this sort of Gen AI world where like the talking heads just keep talking about how that's so important, as I think you'll see in the slides, it's my strong conviction that code reasoning is like the preamble to code action. Code action is anything related to generation, augmentation, removal, all that stuff with code. So what does this mean? What it means is that the more deeply you can reason about code, the wider and deeper the space of the code that you can take actions on. So the better that you can build performance systems, understand the semantic characteristics of the code, this kind of thing. So I may focus on that, but who knows? And maybe if I have time, I'll do a second stream of this tomorrow, just focusing on the second part. But the talk is when is the talk? Monday, this coming Monday, sometime. Here you go. 1 p.m. Pacific time, my time, 4 p.m. Eastern time. And then for everybody else, I'll just let you do the math of whatever that is for your time zone. So feel free to join. And I got to be honest, I'm actually pretty excited to be presenting at this place. This is an MIT seminar thing, and there's several of my mentors that have spoken here previously. So one of them, I saw them in here. I'm a huge fan of Kathy Ulick. She's at Berkeley. She's done a lot of really outstanding work. Served on a panel with her once, and just very impressive. Oh yeah, so here's one of my mentors, Alex. And then thought I saw, look at this, you have Bill Daly on here. That's cool. Yeah, here we go. Morris has been mentoring me for like 20 years. So yeah, anyway, super excited about being invited to give a talk at this place. And these are definitely things that I care about. So yeah, it's some good stuff. And I like their write up here, especially this last part. They're talking about performance and all these things, and also just plain clever hacks. That's cool, right? Like, just keep it real. Sometimes those clever hacks are like, for example, I think in the theoretical sense, perfectly balanced binary trees have guaranteed worst case asymptotic complexity. They have better guaranteed asymptotic worst case complexity than hash tables. But in practice, hash tables tend to actually be like better. A lot of that has to do with the von Neumann architecture stuff, because the trees with the pointer indirection, they tend to they can have more cast misses and things, whereas hash maps, because of the general structure, they tend to be more cache friendly, using contiguous memory and things of that nature. Anyway, so yes, hacks and understanding the difference between what is theoretically really sound versus what is pragmatically very sound. I think that this is an important distinction, and sometimes we forget about this. Okay, cool. So that's my talk, and then I'll talk a little bit about this at the end. So with that, let's go ahead and dive in. Feel free to get your soda and coffee or whatever your drink is, like I have. I've got my stash of Coke Zeros. So let's get into it. We're going to talk about in this talk, first, what is machine programming? Second, how do we reason about machine programming at a very high level? Then, what are some of the core technical domains of MP? I just move this down just a tiny bit. Okay. I've got the dog at my feet too. And yeah, he's also a fan of machine programming. Actually, you know what? Let's wonder if I can make this. Let me try to make this a little bit bigger for everybody. Let's do this. All right, cool. That's a little bit better. I would make it full screen, but I don't want to have my camera block some of the slide. Okay, so we'll talk about the technical domains, machine programming, engineering and researching MP systems, and then exploring these open problems. And there are a lot of open problems. Maybe we'll have a stream on that tomorrow. Okay, machine programming, what is it? Sort of at the highest level, machine programming is really the automation of any aspect of software development, which we've discussed many times. And I want to take a moment on this before we move on to explain a couple things. Like why is this not called ML for code? I think as maybe we've mentioned in the past, but also why is this not called automation, software automation? Because we could have called it that too, right? So the first piece on why not use ML for code, a big reason for that is it's my belief that there's more to the world than just machine learning. And that's coming from someone that is a huge fan of ML and I guess AI, if we want to call it that. And I've been working in that space for 20 years. I love it, but I don't believe in panaceas or silver bullets. I think that the best science and the best technology tends to be a culmination of a bunch of heterogeneous components that, when brought together, provide something really fascinating. So it's not ML for code, it's stuff for code. The second part is it's not just for code. There's lots of stuff in this everything else space that is important to the development of software that has nothing to do with the actual code, like the specification, the requirements, the ability to build systems that are iteratively refinable, the software development process that you employ, all of these things that are related to software development in general, but are not just code. So that's sort of the high level on why MP is not, why I call it machine programming and not ML or AI for code. The other part of, and frankly, I don't actually even care what we call this thing, just to be totally honest. I don't care. I just don't want us to call it the wrong thing. I don't know that machine programming is the best thing, but I just don't know of a term that's better. And so for the time being, I'll just continue to call it that until someone comes up with a better term that captures it in a more precise way, whatever that may be. The second part of why we don't call this software automation is for a similar reason that I mentioned at the tail end of the ML for code part, is we're doing more than just automating software, as in just code. We're doing things to help developers, right? MP systems can be used to shed light on certain things that developers then need to act on. They can be used to improve the CI/CD process. They can give you insight onto the cadence and maybe the goodness or badness of the software development team's velocity. So are they moving at a good speed? Or are they, like these? So these are things that don't necessarily directly have to do with automation of software. It's not the automation of code, but these are things that are peripheral or tangential to this core idea of code. But I think that they're still super important. And therefore, I sort of, my view is in that space of accelerating the development of software, there's a number of things that are related to software development that are not, yeah. Like, for example, I just read something in my newsfeed where Linus was getting a little bit angry about people putting links in Git commits, links that were essentially useless. What does this have to do with automating software? Nothing. But imagine if you had a machine programming system that could help people write commit messages in ways that would make Linus happy, or essentially would make the messages for the commits more useful. You're not really automating software there. You are helping automate the construction of comments. I think that can actually be super helpful. So this is a little bit of background on why this term and what I mean by the automation of software development. As someone that's been doing this for a while and worked on various size teams of one to teams of hundreds of people, there's just a bunch of different dimensions that we care about. Now, for this talk, I am principally going to focus, at least in the open problems, or maybe even a little bit of the background, is be more about code reasoning and code actions. And as we were discussing before, I think that these are kind of like the yin and yang. Is code reasoning is the stuff that you do before you do code actions. You can think of it as like you make the grocery list first, and then you go to the grocery store. The code reasoning, I think, is the precursor, again, to almost all code actions. And if we get away from the hype and realize that Gen AI, that generation part, is predicated by how deeply, how nuanced, how insightful you can be about the reasoning part, it should make sense that the reasoning part is super, super important. And if you are limited in the reasoning, the byproduct of that is you'll be limited in the code actions. Just obvious, right? Like, for example, if you personally have never studied or reasoned about calculus, are you going to be able to do differentiation or integration? Probably not. That would be your action part. And so the reasoning would be the learning of calculus. So you can see how you sort of have to learn and think about stuff first before you can take actions. This is really, it's such a simple thing, but it's, I think, massively overlooked in the world today, at least from the lens that I see, being with one foot in academia and one foot in industry. And I think we need to stop that. I think that we need to remind people, think first and then act. So this is the whole thinking. Okay. And then everything else is all the stuff that's not related directly to code, but I'm not going to talk about that in this talk. I do talk about it in my course. All right, so why do we even need this thing called machine programming? In my mind, there are many reasons why we want machine programming, but at the heart of it are two things. Most software development is not moving at the speed I think that we want it to move at. Being on many teams and I've never seen a team ever in the 25 years I've been doing this. I've never seen a team deliver a piece of software where every feature was implemented that they wanted, all the bugs were fixed, and they were on time. I'm not even talking about being ahead of schedule. I'm just talking about being on time. Never seen it. Never seen it. I've seen people be on time after cutting features or being on time with a slew of bugs and release super buggy software. But I've never seen any team move so efficiently as well as with such high quality that it's just puppy dogs and rainbows, that everybody's happy and we've hit all of our marks and the team's like, cool, we can all take a week off and go to the Bahamas because we're so far ahead of schedule. So the software development speed is the first piece. We just want to make this faster. The second piece is we've got to get speed without quality is, at least for me, is not the answer. And I think we can kind of see that today with the code assistants, is that the code assistants, I believe, at least have the appearance like they are helping with the development speed. I think that there's arguments, although I believe the data, at least the papers that I've been reading, are arguing that even when people, I think we've looked at some of these articles where even developers who perceive that they're moving faster, they're actually moving slower. All of that aside, let's just assume for a second that the code assistants are actually making things faster. I think that it's fair to say, if we're being, again, intellectually honest, and again, if you don't want to take my word for it, you don't have to. Just go read this Get Clear paper or other more recent papers. The quality of code that we're producing today with the code assistants is at a steep decline. And part of our job with machine programming is to fix that. And so you might be saying, well, the code assistants will get better over time. That's what machine programming is trying to do, is to level up the code assistants so they will get better over time. That's actually what I'm trying to say, and many of us that are doing machine programming are working toward. And I do think that there's gonna have to be at least a fundamental shift in the way that the code assistants work if we want them to be used for enterprise software. Because LLMs by themselves, language-only models by themselves, as for anyone that's, I think, an expert in neural networks, knows that these are mostly stochastic parrots. They don't actually have a deep semantic understanding of really anything that they do. They're quite good, I think, at pattern recognition and giving an answer that has potentially the appearance of being right, but their understanding of that answer is absent, I think. And that's a problem when you have to do iterative refinement, and software is all about iterative refinement. It's that whole idea that I've also never seen a piece of software where somebody writes it the first time and it's just perfect. No changes, no bugs, no changes. It's the Mona Lisa, right? That's not how software works. I wish it was, but in reality, it's iteration, iteration, iteration. And this is one of the core problems with language models, is because they don't have semantic understanding of what they're doing, their ability to iterate and improve can be really challenging, if not impossible, without a machine programming system that actually has deep semantic reasoning components built into it. All right. So hopefully we're motivated now on why we need machine programming. We want to make development faster. We want to improve the quality. So now let's reason about machine programming systems as well as software. We wrote this paper back in 2017, just coincidentally with a whole bunch of people actually at MIT. And the three pillars, the point of the three pillars intention, invention, and adaptation, with the foundation being data everywhere. Point of the three pillars is really just to give a framework to think about these systems. And one thing that I want to point out that is very clear to me if you look at the code assistants today is in the space of code assistants, what I often see is the intention will be provided, at least today, largely by humans, although some people are starting to get really clever. They're starting to have the AIs themselves provide the intention, and then another AI do the invention. And I think I saw like a commercial, or maybe it was an Instagram or something, where some guy had two phones and he was having ChatGPT talk to itself, and they were trying to say goodbye. And it like just kept going, where it's like, okay, have a great day. Oh, you too, have a great day. Well, wonderful. Talk to you next time. Oh, yeah, absolutely. Looking forward to it. And just keeps going. And so that would be an example of both of them being like in the intention space. We're just kind of, making forward progress. But one can imagine that you could have a AI that actually is providing the intention, and then another AI that's providing the invention. Where the invention is basically just assembling the code, mostly, at least in this space, at like the prototypical level. It's sort of like the core building blocks that you need for an algorithm or a software system to work. But what you may notice is that the code assistants really struggle with this piece. But when we're writing this paper, our argument was for real software systems, you generally have this intention where this is what you want to build. And then you have this invention where you try to capture the intention. Maybe you capture it correctly. Maybe you don't. And that's where the adaptation piece comes in, is that you then iterate. You are adapting it to make it better, and so it works in this evolving world. Hardware is changed underneath you. Software that you're using is changing outside of your control, or the system itself is just not meeting the fundamental requirements, and so you have to iterate. And what I think can be very helpful is when you look at machine programming from the lens of the three pillars and you consider the code assistants, I think it becomes even all the more clearer that this adaptation part is critically missing. And because it is, a lot of people it's like a halting problem. They're just halted. Because the invention by itself, at least for software, tends to not be, or at least for production quality software. Again, prototypical systems or toy programs, sure. Just trying to sketch it out, proof of concept, absolutely. Just invent it and be like, yeah, this is sort of like what we're trying to do. But if you're trying to build something like Linux or Mentor or Nautica or Windows or PowerPoint, whatever, that adaptation piece is critical. And it seems as though this is, and in fact, even in one of the polls, look, let's meander a little bit here. Let's just bring up GTT actually. And let's just look at one of the polls, so I can show all of you what all of you actually have said to the community about what is the hardest part of software engineering. It's the adaptation part. The overwhelming consensus, at least from GTT, from these 784 votes, 51% of the community is saying the hardest part is essentially the iteration, the adaptation. I 100% agree with this. I think this is, at least from my perspective, this often is a breeze. I think this part can be hard or easy depending on how good the coders were before you. that if it's a lot of spaghetti code, I think this can actually be not super great. But if you have a lot of expert programmers, this can be less challenging. I actually think this part can be tough, at least for a lot of superstars. I know a lot of sort of super coders, and not all of them, but it almost feels like there's sometime a correlation between there's like this joke about I'm going to make this is going to be gender or sex neutral. There's this joke about how the the hotter, the more beautiful somebody is, the crazier they are. So if you want somebody that has like very little crazy, you just need to find someone that's not really hot. And if you find someone that's like really, really good looking, they often are just like nuts. I think something similar is going on here with the supercoders. It's like, and I'm not saying all supercoders, I'm just saying that some of them really, really incredible coder, little bit off the rails, can be a little tough to work with. And so the way that I would probably vote this one is overwhelmingly the hardest. I would rank this second. Again, mostly for the expert, and maybe this is my bias, is I mostly work with the really advanced, professors and stuff, and it's like wrangling cats. When I was running my lab at Intel, and even at Merle with a lot of the superstars, they have their own minds, and sometimes they're gonna do their own thing. Anyway, so the point about all this is that what we can see from our own poll is that the adaptation part is viewed by the community as overwhelmingly the hardest thing, which is why it was on the 3 pillars, right? I think anyone that actually has done real software development, and unfortunately, I think, well, I don't want to say anything bad about the AI code assistant developers, but there's a few different things at play. One thing at play is there's the AI bubble and low-hanging fruit. And so I think it's super obvious to use things like language models to then generate code. So people are like, oh, it's like the gold rush. You just go west and just like mine gold and like just manifest destiny yourself out, where you're just going to make a whole bunch of money and whatever. And who cares if it's the Wild West and bad things happen, right? That's one side. So I think that there's this aspect to it. And then there's this other side. The other side is sort of like people that maybe are in that space, or they deeply understand machine learning. They may not have like a deep and nuanced understanding of software development. And because of that, their emphasis perhaps is not on the core challenge for building production quality systems. Now, I do want to share that I can see an angle where focusing just on these 2 pieces can be a door opening experience for a large majority of the world that can't write code. And so it's lowering the bar to entry, which I think is great. But I think that we need to go further, that we need to have sort of an honest discussion with the community and industry to say, hey, this is actually a first-class citizen, and oftentimes more important than this piece, because this is the focus. And so let's make sure that we're building these machine programming systems that address this. And again, that's, I mean, if you look at Mentor, what does Mentor do? Well, Mentor like principally is kind of sitting in this space, working on the adaptation part. Okay, so that's a little bit about how to reason on machine programming systems. And again, The reason for the three pillars, this isn't to say that this is the definitive way everybody has to think about machine programming like this. It's more just to help people understand how to categorize things. So at one point in time, the analogy I'll give is parallel computing. At one point in time, we didn't have words to describe the different types of ways that parallel programming systems would fail. Parallel programs would fail. We didn't have the language. And so things would just like freeze. And that's what we'd say. Oh, this is frozen. Well, is it really frozen? And we have a word for this, one word, which is deadlock. Deadlock, I think, is an example of frozen. But it's a very specific type of freezing that happens in parallel computing. But there's another type which looks like it's frozen, but it's not exactly frozen because it feels like it's making forward progress, although it's not, and that's called a live lock. Now, it's really important to understand these are two really different types of issues. Live lock systems, the way that you deal with them, oftentimes it's about priority inversion and greedy algorithms and stuff. You fix those in distinctly different ways than you fix things like deadlocks. Deadlocks often somebody's breaking the order of fine-grained locking, and so somebody needs to fix that so everybody follows the same rules, or they're not releasing the locks. Notice that these both look like they're freezing. They both have the word lock in them, but they're different. And so we need language to explain this so then we can talk about it and then reason about it and then move things forward. That's why we have this. That's the fundamental reason for this. Is again, we were seeing in the community that there's just a whole bunch of people doing machine programming, and everybody was kind of like, it was just a potpourri of a whole bunch of stuff, all very cool research, but you have a really hard time wrapping your head around like, how does this fit in the jigsaw world of like moving things forward? So that's a little background about reasoning on machine programming systems, and at least from my perspective, this helps me understand what problems are being solved and what the core emphasis is. And that's really maybe it at the high level. Is it's just gives you a framework to think about things, helps you understand your own machine programming system as well as others, and then also help you see weaknesses, vulnerabilities, pieces that are missing. Again, like the adaptation part. I think when you look at the three pillars of machine programming, and then you look at code assistance, it's like, at least to me, super obvious. It's super obvious that the adaptation part is like second class or third class citizen, and that's not great. So hopefully that gives you some reason on why we wrote this paper. I want to also briefly share some of the first principles that I think are critical for machine programming systems. And this is not exhaustive, but these are some of the ones that I think are really important for machine programming. And this is specific to software. This is saying that given you have software that has certain characteristics that it likely needs to meet in the real world, as well as being hard science and understanding that it is mostly, at least historically, a human-driven endeavor. There's just like all this stuff, and there's privacy concerns. So at the highest level, when we look at this, the things that I tend to care about and I think are super important for the practical adoption of any real-world machine programming system, something that's actually going to add value for software development. It will likely have forward progress or reasonable characteristics in these different areas. So it'll be performant, that the training and inference is economically feasible, And you're not beholden to big tech. Like, I think that most people should be, hey, Amir, I think most people should be like a little bit terrified that the field of AI is largely being viewed in this space where only big tech or people with millions and millions of dollars can train language models. Because what does that mean to the rest of us? Does that mean that we essentially, like, how do you build your own language model without $10 million? You don't. So in some sense, using this model, any individual person is beholden to big tech. Think about if open source was run this way, like the Linux operating system. Linux just wouldn't exist. Many of the open source software systems wouldn't exist, but they don't require millions of dollars in cloud compute to build software, right? It does require a lot of human capital and community, but it often doesn't require, $50 million of GPU usage in the cloud. And so point number one is that you likely want to have an MP system that's performance and it can run essentially on commodity hardware. I think that this is just the reality of it. I also think this is part of the reason why most of the MP systems that are deeply reliant on language models will ultimately fail. Because, as we discussed many times, the economics don't make sense, and somebody eventually has to pay that power bill, and it will likely be the developers. And developers, I think, are going to balk at a $200,000 Claude code bill to build a prototype that doesn't even work. And those prices are, they're, again, we talked about the bait and switch. It's happening. And it's based on my understanding of the economics of this, working in the space of neural networks for some time and sort of understanding the impact and cost of the training and inference on the cloud. This is likely going to continue to increase for probably at least the next decade, if it doesn't just fall, if the bottom doesn't just fall out from underneath it, which I think it probably will. And there's a new article actually that came out, which let me see if I can find this real quick. Yeah. So this article just came out a couple weeks ago. MIT report 95% of generative AI pilot at companies are essentially failing. 95% failure rate for enterprise AI solutions represents the clearest manifestation of the Gen AI divide, and poor integration, a lack of continuous learning capabilities, adaptation, what we were just talking about, unclear ROI, return on investment, rather than subpar AI models themselves. And here we go. Delivering meaningful financial value. And keep in mind, this is before the costs of using the language models have like fully skyrocketed. It's just going to get likely more expensive. And the reason why it will get more expensive is Dennard scaling ended in the early 2000s, which means that we can't, it's very challenging, if not impossible, to continue to increase computational efficiency while keeping the power utilization flat, right? So there was a time where you could just get more bang for the same buck. You could spend $1 and initially you're getting like a Big Mac, and then move forward, spend $1, you get 2 Big Macs, spend $1, get 3 Big Macs. That's great. That's wonderful. If compute was following that same principle today, which I think a lot of the language model people, for some reason, either don't understand or they don't care. If it was following the Dennard scaling today, then it could be that compute would just naturally progress to the point to where the overhead that's necessary for the training and inference of the language models would be ameliorated by the advancement of computing hardware. But unfortunately, Dennard scaling ended 20 plus years ago. And because of that, you'd have to essentially fan out, which basically means it's going to be super, super expensive to do this. In my mind, that basically tells me this is the wrong core technology. It doesn't mean that language models don't have value. Again, I've said it like hundreds and thousands of times at this point. Okay, that's an exaggeration. I've said it at least hundreds of times. I think language models have tremendous value when they're used in small stochastic problems, as they're used in soft science and used for problems that are outside of the space of hard science. Unfortunately, software development is the space of hard science because software programs often require deterministic execution. You press the start button and the thing starts. You press the end button and the thing ends. You press the record button, the thing records. Determinism. Which is a second core property that is critical for MP systems. I do think that some part of the MP systems, when it's just brainstorming, stochasticity can be really valuable. But these are sort of auxiliary, high-level things that they're supplementary. They're not the core mathematics that drive the system. And this is the second reason why the language model approach, at least for software systems, is likely doomed to fail. The third characteristic is you often want these systems to be as close to objective as possible when you need them to be objective. And what I mean by that, what I mean by objectivity, is that the results are mostly supported by objective reality, something that's scientifically verifiable. 1 + 1 = 2. And not 2 most of the time, 90% of the time, but then 10% it's like 7 or 48. That's, I think, not going to do it. Again, not for hard science. And so that also needs to be a core property. The next one on the list is it should be flexible, I think, in where the system is run. So if you have code IP, you generally want these systems to be able to run on-prem behind your firewall where no one else can see your code. And that rules out the current systems that we're using today, except for the huge trillion-dollar companies like Apple, Google, Microsoft, Amazon, blah, blah, blah. For any of the smaller companies that don't have the ability to run $100 million cloud infrastructure, but they have code IP and they need it to essentially be in an enclave locally on-prem, you want to have an AI system that can support that. It's critically important. And then the last piece that I want to share that is also part of the first principles is that I believe the MP system should reason about more than just the code itself. I think that they should reason about a bunch of other things. And one of those things is the societal ramifications of the system that you're building. What does that mean? How is the development team meshing? How many contributors are there? Are contributions happening actively? Are you seeing malicious users? Are you seeing developers that are sort of just continuing to introduce really bad things? These are, we coined this term socio-software because Mentor found the existence of the XC utils backdoor attack for the Linux kernel not by looking at the code, because the code was never directly checked in. It was just object code inside of an encrypted tar file, as I understand. But by looking instead about the social aspects of that library, which indicated, I believe, that Jiatan was having weird, anomalous behavior for a contributor. And when you look at more than just the code, I think that these are the types of things you can observe. You can find other things that can be improved with the software, as well as things that are being done really well in the software that are not related to the code, like the team cohesion, all of this stuff, who the superhero coders are, making sure that those people are happy, this kind of thing. I think again, it could be very important to have this type of analysis. I'm not saying that all MP systems have to have this, but I think that MP systems in general will likely be better if they can expand their horizons to reason about more than just code. All right. We only have 2 more slides to go, and I'm starting to feel a little bit under the weather, so we're going to try to speed run these. As I was mentioning many times, we don't call this ML for code because there are these other pieces. So here's the machine learning piece, which I do think can be great. I think that you want to use machine learning because it can learn things that are very nuanced, that are hidden in the data, where the algorithm itself may be very challenging to express in the way that we have programming languages today, but it can be learned. And so we want to use it in machine learning in that capacity. But there are minimally these other 3 domains. So at a high level, the ML part will help us learn essentially the algorithms that we would historically write ourselves. They will just learn this from the data. And a big reason why this can be valuable is that this can, in theory, scale. So we can learn different things, different algorithms, different whatever, in a much wider space, potentially deeper space, than if you programmed it manually. Excellent. But that by itself is not sufficient, because if you don't have a deep understanding of programming languages, you may not be able to build the right ML system to semantically reason about the code. I think that's part of the reason why a lot of the code assistants are kind of a little bit subpar, is they don't deeply understand the semantics of the PL or the PLs that they're working in. So there's ways, I think, to capture semantic information as well as intentionality of the code, which then tells you a little bit about why that software exists and how to better construct it. That can help the ML system. Secondly, software engineering. If we don't deeply understand the actual art of software engineering, we are likely to solve the wrong problems. So we're spending all of our time on the generation of code, but not realizing that, oh, wait, one of the hardest problems and where people are mostly spending their time is actually adapting existing code. Maybe we should try to focus on that problem. And it's not to say that people haven't thought that. I think some people have. I do just think that it's so much harder that a lot of people that are seasoned, maybe they turned away from it saying, I don't know how to do this. Let's just start with a blank canvas. It's so much easier. And I get it, but that doesn't elide away the problem that we need systems that are adaptive. It just means that people are just solving sort of the easier problems because they're using what's laying around on the table, which is good as a starting point. But now that we've got the starting point, let's start focusing. Let's not turn a blind eye to the core challenges that we know exist. And then the third piece here is system architecture. This is really important to build these systems so they're efficient. Goes back to that performance piece. If you don't have a deep understanding of systems, then maybe you're writing your entire MP system in Python or JavaScript. And again, that may be okay for a single client. But when you're building an MP system that's going to maybe iterate on billions of lines of code, um, maybe you want something closer to the bare metal, and maybe you want to understand how to most effectively utilize the hardware, or as I like to talk about it, CDC, compute, data, and communication. Those are, I think, the three areas that you generally need to have good system understanding on to build highly effective MP systems. So that's the way that I think about this. These are the other domains and part of the reason why we don't call this ML for code. And then lastly, when we are building these systems, either for research or engineering, I'm of the view that, and this is meant to be somewhat exhaustive. By the way, this is non-exhaustive. There are other domains that I think are important. These are just the ones that I think pretty much show up all the time. But they're, depending on what problem you're solving, you're probably going to have other domains that are important to you. This slide, I think, actually is exhaustive. And the reason why I think it's exhaustive is there's sort of two fundamental ways to build MP systems. You can do it the traditional way, which is rules-based, which basically the algorithms are handcrafted and we have the precise code, or you can do the stats-based, which is it's learned. And so these are sort of like the two fundamental ways of doing things. If you think about machine programming systems as algorithms, then the algorithms can be learned by the machine, or they can be learned by the humans. The rules-based are essentially humans have learned it and are saying, these are the rules based on my human knowledge, so we should do these. Stats-based is basically saying, humans, I don't know maybe what the rules are, I'm going to use the machine to learn it, and it's going to statistically learn the rules that it thinks are best. Both, I think, can be highly effective. The stats-based is basically the machine learning side. The rules-based is more things that are precise rules, like what you would find historically in compilers, intermediate representations, formal methods, all that stuff. Most of the best MP systems that I've seen are a fusion of both. And unfortunately, what I see today is almost a disproportionate number of systems are focusing on this side as if this side like doesn't exist, which is very strange. It does exist, and it has a lot of benefits. And so we can lean into this side and use this, and it's not a bad thing. In fact, oftentimes it's super necessary, especially if we want to provide certain types of guarantees that are not possible with statistical systems, right? Statistical systems are probabilistic in nature. If you want something to not be probabilistic, you just sort of like can't use a stats-based system. It needs to be rules-based. So if you have systems of the MP that you want it to be like, okay, it's no longer statistical, it's no longer probabilistic, it's just like gonna follow core mathematical precision, then it almost must be rules-based. I'm trying to weaken the language here because I know a lot of the Jeters are super smart, and you might come up with a corner case where you could do a stats system and it's like guaranteed to be correct. Probably for the precise data set that it's trained on, but if you are out of distribution, then probably not. Yeah, and so when you're trying to build a real system, real MP system, or a research one, these are basically the ways that you do this. And so one concrete example of this is neurosymbolic systems. The neural part is the neural network. That's the stat-based. The symbolic part is the rules-based. So that's the rule side. And that's an example of using those two together. Okay. So that's basically what I have for my upcoming talk. I don't have this part yet. And so we breezed through that. That's great. Uh, I wanna leave all of you with one final piece here, that for those of you that have stuck around, or if you are watching the video recording and maybe you jumped to the end, however you got here, I'm glad you're here. I want to share that some of you have asked these questions, like, how did you create Nautica? How do you end up teaching at this place? How do you get invited to give these talks? And I want to share that, like, there's a lot of confusion, and sadly, I think it's partially it's this hype media that we live in today, where they try to sensationalize things that are just really silly. Like, the only reason why something great happens is someone has like a 200 IQ and they're a child prodigy, and just they're born great, and the rest of us can't ever achieve that. Uh, I personally was a super late bloomer, right? I think, as many of you know, in high school, I mostly was blowing things off for a very long time. My graduating GPA for high school was like a 2.7. My undergrad was just at a state school, maybe not even the top 100 universities. And yet I teach here now, and this is not my first invited MIT talk. I've given like several of these, and I'm not sharing this to flex. I'm actually sharing it for the opposite reason, is that in my view, on the reason why these things happen, it has far more to do with me just doing small footsteps and being consistent than me being smarter or perfect or whatever. In fact, uh, I'm often the dumbest person in the room for the circles that I run in, and I love that because I get to learn from all these super smart people. Uh, I'm of the mindset that the reason why I get lucky enough to give invited talks at places like this, teach here, run this place, is I'm just really consistent. I just try to be super disciplined and take small footsteps every day, including today. So, right, like, it's Saturday night. I think most people are probably taking the time off and maybe Netflix or socializing or world tour. And I think all of those things are great. Like, absolutely, if that's what matters to you, do those things. But if you want to do really meaningful things, if you want to have incredible impact in whatever domain it is you want to have impact on, not machine programming, maybe it's just programming languages, maybe it's playing the violin, like whatever it is, I'm of the strong conviction that as long as you make small footsteps consistently, you have a huge amount of discipline, you can achieve these things. And this type of thing is much more important than having a 200 IQ. In fact, I think it was Albert Einstein that said, it's not that I'm smarter than everyone else. It's just that I've sat with these problems much longer than most people. That's exactly how I view these things personally. Is it's not that I'm smarter than anyone else. It's more likely that I've just sat with these problems like I am right now on a Saturday evening. And I'll be doing the same thing on Sunday. And I was doing the same thing Friday night than other people. And that's what really, I think, leads to people having incredible impact and doing highly meaningful things. So if this is something that you want to do, it's the formula is, in my mind, very easy. The execution of it and the discipline of it is extremely hard. This is where I think most people fall off. It sounds super easy. All you have to do is just be hyper disciplined and do this every day. And then it is the actual execution of doing that. Most people can't do that. And it's really just a choice. So, of course, there's a bunch of other factors. I'm not trying to oversimplify it. And believe me, I know that I'm super blessed and I'm deeply appreciative of all my blessings. super grateful. And I'm also super grateful to all of you Jeters for supporting me on the platform and listening to me ramble constantly about all kinds of things. But I wanted to share this, especially for people that are really seeking to do great things, but might be getting a little bit confused due to all the noise that's out there in the world today, especially from hype media saying, this is what matters. Follow this 7-step plan and you'll get there. No, it's just hard work. Like, it really is just in some sense hard work. And it's doing the hard stuff. It's doing the boring stuff. It's doing the quiet stuff. It's about spending the weekends learning and growing and studying and learning while everyone else is out there partying and doing other things. And again, I have no issue with that lifestyle. But for me personally, that's not what I want to do. I want to do stuff like this. And I want to give talks at places like this so I can work with really incredible collaborators that will teach me things and we can all function as a community. And that's part of the reason why we have Goju Tech Talk. So with that, thanks everybody. I appreciate all of you watching, especially if you got to this point. It's fantastic. And I may do another stream tomorrow with the second half. But I think I'm coming down with a little bit of a bug, so I may not, but we'll see. That said, I'll drop a link to the actual MIT Fast Code talk that's happening on Monday. And I think, it's open to the public. So if you are interested in seeing the shorter version, actually, I think it's an hour. And it took me about an hour. So maybe it's about the same version. Anyway, if you want to see it actually happening real with some of the professors and PhD students and all that stuff, feel free to dial in. We'd love to have you there. So with that, have a great evening, Saturday, Sunday, wherever or whatever day it is, wherever you are, and keep doing all the great things you're doing.